Okay, welcome Year 12. This is the presentation that I made on errors and titrations. This is the third time I've done it because I did it once in class for everybody who was there on Tuesday afternoon. Then I recorded it again today and then I left it at school. So this is my third one. I hope you get to watch it. I'll probably be even quicker than I was in the last few. It just give you the benefit of what I'm talking about with titrations in and some of the errors that we can encounter with them, so you can use this to critique your method and look at ways of improving it. So first thing to do is think about what an error is, and basically we're going to they're the difference between our observed values and also then what's true. So for example, in your analysis, there's the actual value of what should be in there versus what we're measuring in our experiments or through our titration in this case. So if we make errors, that means that our results will be inaccurate. They could be misleading. They can even misrepresent nature. We also have those standard values that you see us using, where they're our best approximations or descriptions of what's going on in nature. So we have a lot of standard tables. You'll notice they're at 25 degrees Celsius, standard pressure and temperature. Sorry, that's standard room temperature, but standard pressure. And that's valuable because everything else can be compared to these values that they've made under the very strictest sort of conditions. So they've measured in that case. So there's three types of errors. We have systematic, we have random, and we have blunders. Systematic errors are things that we can actually identify the cause of them, and we can then eliminate them, stop them. What you find with a systematic error is it will be a value that are higher than should be or lower than it should be. And the thing to remember is sometimes you don't know what it should be. Okay, so it's being aware that what you might be measuring isn't actually what's going to be happening. So with when we're doing our titrations, it could be possible that we are measuring the volume we're actually adding in is slightly more than we need to or slightly less. And we're continually doing that, which means that our value will be off either on the upper end or the lower end. It's not varying both sides. So this is the systematic error. 4 things that it can come from. It can be our instruments being poorly calibrated. Calibrated means set so that they will record the right value each time. You remember we had to do that with the pH meters. Observational. So this is parallax reading. Parallax error is where you can't quite see where a line is. If you look at your meniscus from directly straight ahead, that's the way to read it, not from a bit below, not from a bit above. So it's important to move your burette so you can read it properly. Environmental, so problems with your electrical power, which is not relevant in this case, but it can be if you're using a scale, or if the scale itself is actually just a bit defective and it's not measuring properly at a certain level. Just so you know, we are making sure all these things won't be a problem for your exam, but it's just important to realize that these are things that mean that our measurements are never going to be perfect. The last one, theoretical, is really important in looking at titrations because we actually are simplifying the reaction between acids and bases when we're doing a titration, and that is that the equivalence point where the moles of our acid and base are equal. So they're in that, when I say equal, I mean in stoichiometric ratios. It can be a 1-to-1, it can be a 2-to-1, it can be a 1-to-2. You know, you need to go back to the equation and see how many moles of the acid are needed to neutralize the base. Okay, so the equivalence point is when they're at equal, when they're balanced, when they're in equal quantities or equal proportions is the word. But we're actually not measuring, we're actually not seeing that. We can't see that particular value. And that's why we're using indicators to see where that color change, to show a color change at the pH where that's likely to be occurring. And it's fairly, it's not completely inaccurate. There's a lot of accuracy to it because we pick the indicator that's going to do the color change when we're, when the equivalence point is near. So we always pick the indicator based on where the color change of that indicator is going to change around that equivalence point. Okay. I'll go back into this in a little bit more, and it may be some things that people want to ask questions on. But the simple thing is that endpoint and the equivalence point are slightly different. And that is a simplification of the system. And that can actually be another systematic error, okay? Because you're always going to be measuring it. In this case, possibly putting more, adding more from the burette than you need because of how long it might take you to see the endpoint, just that little bit extra. And so that's one of the flaws. But if we understand it and recognize that, we can still count this as a reliable technique, okay? It is really important to know that it's still a very accurate one in this sort of sense. The other errors, random errors. So these are where you've got fluctuations. So from your recorded values, they're going up and down. So half your measurements are higher, half your measurements are lower. We can't always know where they come from, but some examples of where they can come from are just your observational issues again. And this is a bit different to the last one, because if you're reading from the wrong angle and you're consistently doing that, that would be a systematic error. But observational, when you're looking, especially when the meniscus is between the lines and just the curve of the light, like sometimes that's really hard to pick if it's 22.1 or 22.15. You know, those sort of errors is what we're looking at with observational. So reading a scale on the measuring device to the smallest division, which in our burettes is to the division of half, sorry, I should just say 0.05 mils, okay? So half of a tenth of a mil. The other one is like environmental issues. So again, with our scale, not saying the scale's all functioning properly, but if you're moving too much around it, the fluctuation, you'll notice that the scale goes up and down, and its measurement tends to go up and down by a couple of values, so 0.01 or 0.1 of a gram. So they're the sort of things, they are random errors, and that's again something we can know and we can do something about. The next slide talks about the comparison between them. So random errors, we can actually find out the number, quantify them, look at their size by statistical analysis. When we do averages, we are trying to find the middle number. So, you know, kind of taking away that upper and lower variation that happens. And we can look at the spread of those numbers. If you do statistics, this will sound familiar, the range of those numbers, and we can use that as going, well, our variation is very wide, or our variation between the upper and lower number is very small. And so if it's smaller, it's obviously going to be more accurate, okay? And there's less uncertainty in that. I'm not getting you to do uncertainty in the exam. I haven't gone through it. I just wanted to go the idea of errors so that you can actually think about how you can keep your method as accurate as possible, but also how you can appreciate reasons why you may not be able to get close to the accurate value in the exam. And I don't want you to stress about that. I want you to be able to write about it. Okay, so random errors, like I said, we can determine it. We often do an average, and they often vary around that average, okay? So that's why we do the average, because that's likely to be the accurate value, to the actual value that we're looking for. And so the other numbers around are just our variations. However, if you also have a systematic error, that point that you're looking at, that you think like the average, might actually be off from what the real value is, okay? So it might be higher or it might be lower, okay? So the volume that you're adding might be greater than it should be or might be lower than it should be, okay? And that's not something you can know unless you're actually given an absolute value, and the actual value or the exact value that you can compare to, which you will in the exam, and that's why I want you to know about this. So blunders are mistakes that you make: write the wrong value, misread the scale, not write a digit, add too much acid, or put in the wrong indicator. All those things, they happen. So the best thing is to go, well, if you can't salvage it, then just leave that one out, do another round. You have enough that you can make mistakes in the exam, and you'll have time and be able to go back and fix things up. So don't include a blunder in your, you're allowed to like leave that off your statistical analysis because it doesn't fit. It was a mistake on your part, and it's not, it doesn't have to be counted in your titers for the average value of liquid solution that's let through the burette. Okay, so that's just the idea of blunder. You don't have to keep that number in the value. Okay, so I gave you guys time in class, and right now it'd be really useful if instead of just watching this, you pause for a moment and think about some of the things I've said and what other errors could occur during a titration. Then think about, are they systematic or random? Because when you know what they are, if they're systematic, you can kind of work and either try and minimize them, or you can reference that in your discussion. And if they're a random error, you know what analysis you can do. You can also try and, if you can identify it and try and fix that, you can also have a look at when the number does vary a bit to recognize it should be the middle value rather than the upper and the lower. Lastly, I want you to think about what the effect of these errors are on your titration values. So pause the video now. All right. These are some of the ones I had. I'm sure there's other ones that you can look at. You've got misreading volumes, different ways, whether it's a systematic or a random one, just not getting the exact measurement. Writing down the wrong concentration value, using the wrong technique, especially for rinsing, which will change your concentrations, making a judgment of the endpoint, the fact that the endpoint and the equivalence point are different, and that's what I said, excuse me, our theoretical understanding is actually that little flaw in that system. It's not so bad that we don't use the method at all, but we do need to recognize that by the time we reach endpoint, we may have put more solution in than what we needed for equivalence point. And it's a very small amount, because you noticed when we did titration curves, the line was very narrow, and it was a drop or two, and then suddenly you're past the endpoint. So it's not giant amounts of solution, but this technique is looking at smaller amounts of solution, and half of 0.1 of a mil can still be significant, especially when we're looking at dilute concentrations. Okay, if your glassware is miscalibrated, so it's not actually weighing or measuring out 25 mils or weighing things correctly, that's one of them. Your equipment might be broken or not reading correctly. Your indicator used the wrong one. The fact that your devices do have their own limitations and may be out every now and then. The temperature that you conduct your experiment at will affect the acidity of solutions, because we know that it's an equilibrium reaction and it can be temperature dependent. And I'm saying water at 25 degrees Celsius, that's when you've got your water constant, but at different temperatures that will shift to become more acidic or basic depending. Also the solution itself, diluting it or mixing it by incorrect technique, carbon dioxide from the air being absorbed into it, changing the pH slightly, and evaporation of the solvent. So some of that water leaving will then increase the concentration. They're all things that can be errors, and they're not likely to always happen. It's just good to know that these are some things where your results can be affected. So if we look at it in the classification table, you can see I've put kind of misreading volumes in all three. You can make a blunder at it. You can misread volumes randomly by just misjudging where the half point is, between the 0.1 mil. Is it on the line or is it between? That's one. That's random. Systematic would be continually looking at from a lower angle and then not reading quite exactly on what it should be. So the endpoint and the equivalence point being different, it's also systematic. Like I said, the endpoint's what we can see with the indicator, and so we pick our indicator accordingly, where the equivalence point is when they're actually in the molar ratios in the equation. So the amount of moles of acid and base are proportional. Okay, judging endpoint's another one, slightly different to the point above, but people's perception of color can be different. So your perception of whether it's just pink or good pink or less like that, that itself is going to be a systematic error, because you may, and you will judge it differently to another person. Okay, so that's based on kind of personal measurement or personal judgment, and that can be different between person to person. Okay, you've all had really good practice, and I'm confident that you'll be able to do this. You won't find this too difficult, but it's important to know that that can be one that you can talk about. The glassware calibration, you know, if there's something else it could be, that can be one. Some of the other things, I think I've pretty much talked about all these ones before. If you're using the wrong indicator, you won't be able to see endpoint, okay? With the indicators, it's really good to remember that when we mix a strong acid and a strong base, they're equal strength. So basically, it's all about their conjugates, the conjugate acid, the conjugate base. For those are going to be basically very crappy or very absolutely useless acids and bases, and you end up with a solution that has a pH of 7. Okay, and I'll go into more of this after the exam. It's not this much detail, it's not what I need you to do, but you know then strong acid, strong base, bromothymol blue should go to a green in between. If it's a strong acid and a weak base, think about the tug of war. Between the middle point between that would be acidic, and that's where methyl orange does its color change. So that's its pH change area, and that's where the equivalence point will be, because from that weak base you've got, it's also got a weak conjugate acid, and so therefore your solution is slightly going to be acidic. For the base, you have a strong base and a weak acid. Again, your weak acid will also have a weak conjugate base, okay? And so your end solution will be slightly basic, which is why we use phenolphthalein, because phenolphthalein has a pH color change in between 8, 9, or 10 pH, and that is where a weak acid, weak acid, strong base will have its equivalence point. So we use a chemical that will change color at that point, and that's what we call our end point. Okay, so it is important you guys can use that language when you're talking about the indicator you're choosing. Okay, so know whether you need methyl orange, bromothymol blue, or phenolphthalein. And it is actually in the notes that I have given you and written down a few times. So make sure you're checking that up. All right, so minimizing errors, we're towards the end here. Firstly, identify and try and control some errors. Think about, you know, I've been helping to improve your method, and you guys have gotten much better at and more confident in doing this. But in the end, if you don't notice it and you see that you're off, this is something that you can then come back to. Think about some of the other errors that maybe were out of your control and use those to explain why your value could be different. Random errors. This is why we often we take our averages of multiple trials. And if we're going to talk about how accurate your method is, we look at the fact that your random errors, as much as possible, they're kind of in a short range. Okay. For blunders, you guys need to not stress too much. I know it's an assessment task and there's a lot happening, but I've seen you all do this and I know you'll be fine. So you just need to take care with what you're doing. Remember to breathe. If you make a mistake, get up, brush yourself off, and keep going, because you can do this. So in looking at errors, we consider about accuracy and precision. So accuracy is the difference between what actual value is and what you measured. And so to try and improve your accuracy, you want to minimize your systematic errors. For precision, you're looking at the variation when measured the same thing repeatedly with the same device. Okay, so doing a titration over and over again, those little variations in the volume that you're getting, the titers at the end, that is your, that's based on your random errors, and that's looking at your precision. And of course, you want the difference between them to be very close. You want them to be concordant, which means they are the same value each time, as much as possible. So this is a diagram that is frequently used to show this. There's accurate and precise. The target in the center is representing the actual value. And you can see in the diagram talking about accurate and precise, all the points are on the target center. They are close together. So it's accurate because they're on the center, and they're precise because they're close together. Their variation is very small. At the second one, they are still very close together, which is making them precise, okay? But you're off center. You're not right near where the value is. This is where the systematic error is in there, because while they're close together, you've got the random errors quite small. You have missed where the center of the target is. You've missed the actual value, okay? And this sometimes happens, and you can talk about, well, why is that difference? What could these errors be that you need to account for or try and fix next time? This one here, you can see that the dots aren't very close together. There's some in the hoop, but not all of them. But they're all going to come up with the same average, which will be the actual value. So they're accurate still because they are around the center value that is the actual one, but the precision is low because the variation between each of these is quite high. They're all different values, and if I had a range, you would find that range would be larger than the ones in these two for how far apart the numbers were. And lastly, the last one, like they've got 1 out of their 7 tests here correct. They've completely missed all the other ones. They're very far apart. They almost don't seem to have any pattern to it. And there'd be no way of using this information to actually figure out what the actual value is. So, you know, sometimes our precision might not be working very well. Sometimes our accuracy might be off. And if we can get both, that's excellent. But at least make sure you're working on one, and you've got your values of the titration, having them close together, that will give you precision. And so that's something you can that you can talk about. And, you know, if your value that you calculate for the aspirin tablet is the same or similar to the one that I give you, then you'll be able to talk about your accuracy as well. Okay, think about what you could do to improve it if it isn't as high, and make a judgment how well you've made that. So the way to calculate your percentage error, which is what I'm going to ask you to do, is to look at the value that you've measured. We call it the approximate value. Subtract your exact value, and the absolute tells us that if that is bigger than this, it will be a positive number. But if VA is smaller than VE, you still make it positive. You don't want to know whether it's negative or positive. You just want to know what the size of it is. And so for percentage error, the same thing. You look at the difference between your approximate and your exact value, and divide it by your exact value. So you're looking at it as a fraction of the exact value. How close to it have you got? The smaller your number is here, so the closer you are, so 0 to 1 would mean that you would have like minimal errors, and that's what you want to aim for. Okay. Look, I will be looking out on Google Classroom. I get alerts when you put messages there for me, so feel free to do that for the next couple of hours this evening, and I'll try and get back to you as soon as possible. Okay, guys, don't leave it too late though. Also, make sure you have a rest and be prepared for tomorrow. And I'll see you all there, labs 5 and 6. Okay. All right. Good night.